So as I mentioned that previously, we actually prepared a structural file and create a topology file and then put the topology file on the MD. So we do all this step minimization, equilibration, and then production run. After that, the final output would be a file with uh, a trajectory file. So if you couldn't open the trajectory file with any software because it's too huge and maybe it's in some actually system, it's about 100 terabyte. You see, you couldn't even download that file or transfer that file between the cluster and your system. So we need to process these trajectory first so that we could start analyze that. The very first analyze that you need to do is that actually you need to use the auto image the comment. So as I mentioned that before starting an analyze, we should generate a stripped trajectory and reorient to the center, because during the, do you remember that we actually create a box and fill the box with the water molecules and ions so that we have a dynamic system. So, and then put the protein in the center of the box. But during the simulation, these actually protein, that's protein of the interest, would be moved. Yes, so we need to after the actually finishing the MD run, we need to reorient it, these protein in the center of the box. Yes, so this is the first thing we need to do. And another things that, as I mentioned, these trajectory file is too huge because we design a box and fill it with the water. All these water molecules would add up the process and calculation. So in many, actually, in many systems, we don't need any water because we already did the simulation, and after the simulation is done, we don't need the water. But in the case of the KRAS, we need these water molecules, some of these water molecules. But in most systems, we don't need any water. Sorry, I am in a lab, so I have no idea how it's noisy. Sorry for that. Okay, so we need to, for many systems, we need to remove or delete this water or strip this water. And also we don't need these ion that we add to neutralize the system. Yes, so we need to delete that too. So it's actually reduce the size of the trajectory file and actually leads us to do the other calculation much more faster. So we create these comments or bash files so that we could actually process the raw trajectory to the fixed trajectory, so that we could actually strip the water, strip the unnecessary ions, and then reoriented the protein on the center of the box. Yes, so the first thing that you need to actually use when you start analyze of the system is this comment, CPP traj. This is actually the things I mean the program that Amber used to analyze. You could use these for analyze of the system. So first thing you need to type this. First thing you need to load Amber, a specific model or specific version based off the previous video that I explained how to load Amber and how to use the specific model with a specific version, and then type these comments, CPP TRAJ. After that, you actually enter to the space that you could type the specific command so that Amber recognize that command and process your trajectory file and give you your interest data. For example, if you want to give the H1 pattern, you could have a specific, first you need to type this and load the specific command, and Amber gives you and process the data, process your trajectory file and give you your interest, your data that you want to, okay? For example, H-font, DSS analyze, or distance between two residue or atom or something like that. So the first thing that Amber needs to for processing the trajectory file and for analyzing the trajectory file is that you need to load a specific actually topology file that based off the system. So for using for actually loading the topology file, you use this command harm and then name of your topology file that you already actually created before starting the MD. Do you remember in the first step, we first prepared the structure and then use this structure to create the topology file and then use this topology file to create a trajectory file. Yes. So first we need to load a specific topology file. So the command that we use to call the topology file to be loaded is that command parm. And after the topology file is loaded, you need to load trajectory file so that we need to actually tell Amber what trajectory you want to be processed. So with trajin file, you just simply type trajen space and your trajectory file. And then we use that automage command. This is a command that we use to reorient the system. The system, the reoriented system, the protein in the center of the box. As this command automatically center and image the trajectory with periodic boundaries. And as I mentioned, in most of systems, we don't need water for analyze. So we could strip or remove the water. So with the strip command and the space and this shape of the command, you could actually remove the residue. For example, in that case, I removed all the water molecule if you want to. And then, as I mentioned, we don't need any of these unnecessary ions, so we could use it. And in the final step, we trash out and you name a new MD, no water, and NC. With that specific type, it's called you that create a new trajectory so that we process and use this new trajectory for further analyze. So in the first step, you need to process your raw trajectory because in the raw trajectory, there is so many unnecessary ions and unnecessary water molecule, and also maybe the protein is moved and this no and something like that. So first you need to actually process the trajectory file and create a new trajectory file. So using this trajectory as a trajectory gets us to be sure that we have a good starting trajectory for starting the analyzing. So another thing that I want to actually tell you, I mentioned that you could use auto image so that it's automatically center and image a trajectory with periodic boundaries condition. So you could use send these comment instead of this orientation, this comment actually center is mentioned that Amber is told Amber that center this residue mass origin. This is your protein. that is starting from the number one residue and end with this residue. So with the centering, you don't include water and ion or something like that, just number of the residue number of the protein. And then you first, and after that, using that comment, image and origin central family are common. If you don't want to use autoimage, because autoimage, specifically when you have a protein with two domains, some things autoimage work weird. So for most of the system is work correctly and good, but for some of the system, specifically the protein that have two or more domain or chain, it's better to use that command. So this it gets Amber not be confused about what molecule. There is two different chain of the molecule on protein. So what should be center? So this is. So if you want to use this comment, be sure that use a specific familiar, because this is the type of the box that we use. So it's necessary to use the familiar comment here too. So another things, after reprocessing the trajectory, we need to actually do a specific and very important analyze, RMSD and RMSF. For the RMSD, is really important. The first analyze that we actually should do after processing the trajectory or raw trajectory is that we need to do this RMSD analyze, because we need to be sure that our system is converged. So there is no other things that you need to be changed or something like that. For example, so RMSD or root mean square deviation of the atomic position gives us the value or average distance between the atom of superimposed protein. What that means? For example, so we have a starting point. Yes, before starting the MD, we have a specific position for each atom. Yes, after we put this protein on the MD, this protein would change. All the atom and the residues could change. Yes, RMSD actually get the average distance between these atoms. First, it fits every actually step to the first step structure, which is superimposed. Superimposed means that actually you put two things together. That's these actually residues fit together. I believe I show you how to superimpose work after the actual meeting in the Schrödinger. So the RMSD should be stabilized before doing another thing. If the RMSD is not stabilized and you have two fluctuated things, you need to extend your run, because it shows you that, okay, your system is not converged, it's still moving, still there is another actually change happening in the system. So your system is not realistic anymore, because if you actually start analyzing or keep analyzing a system with unstable RMSD plot or RMSD variation, your data would not realistic, because there is so many, the system is still changing, the protein is still moving. Okay, so if you actually do the analyze on this system, you miss lots of change. Okay, so if the system is not stable, you mean the RMSD is not stable, this means your system is not converged, and you need to extend your simulation so that you get the converged RMSD plot. Okay, for the RMSD and RMSF, RMSF actually show how the atoms, how the residue or atom could change during the simulation. So for the RMSD and RMSF, for the RMSD, the first thing you need to actually call Amber to load your topology file, and we use the new process trajectory file. And this is the comment for the RMSD. So this is means to first, the first means that the first starting structure is your reference. So it's called Amber that fits all the structure, all this structure and PDB during these trajectory file or steps on the first structure and calculate RMSD. Okay. So after that, and this means that actually means that backbone of the protein is important. We don't care about the side chain right now. And this is the RMSD output for the RMSD. This means if you actually put this comment, this value, this plot the RMSD of the Amber trajectory in time units. So in time unit, if you actually remove that, it's correct. It's nothing would be changed. That gives the RMSD based off the frame. Okay, so to first means the first frame would be a reference for the calculation of the RMSD or superimposing, and each frames would be fit or superimposed to the first frame, and then calculate the deviation from the first frame. Okay. So the RMSF, first thing is just similar with the RMSD. Just you need to actually load the topology file, load the new trajectory file, and RMS first, and you need to have a average between the old frame and then run, and this is the calculation. So it's still on a backend of the protein. So another analysis that is important to be done is H-bond. So sometimes actually when you dock a drug on a protein or mutants residue on a protein, you want to know how the protein reacts to that part. Sometimes the protein dynamic would be increased due to breaking some of these hydrogen bonds. So you need to calculate the hydrogen bond pattern, because hydrogen bond is actually plays a very important role on the dynamic of the protein and interaction between the residues. For example, if you lose in just one strong hydrogen bond between, for example, a loop or a helix, a residue on a loop or a residue on a helix, if this broken, it means the fluctuation of this loop would be increased. So it's heavily impact on a dynamic of the protein and cause, for example, it plays a very important role in cancer or unregulated protein. So this protein could be actually named a cancerous protein. So this is important things that we need to care about. So finding a hydrogen bond pattern using these analyses is really important. So for the hydrogen bond analysis, just a start, you need to start this program by typing simply CPP-TRG. And this, unlike RMSD and other analyze, you need to load a specific topology and a specific trajectory by following commands. And then first, the first hydrogen bond command, you need to actually tell Amber that first you need to calculate the hydrogen bond pattern between all the residue, I mean solid and solid. And then if there is any hydrogen bond between the residue and the solvent molecule, you just need to calculate that. And also you need to find or calculate the hydrogen bond pattern between the bridge hydrogen bond. That means a solvent bridge a hydrogen bond between two residues, okay? So you need to care about these, and you need to actually type and call Amber, tell Amber how to calculate that. So we're using that comment to actually calculate the hydrogen bond. So this is the hydrogen bond between the solvent and all the bridge faulty molecule and all this residue between the hydrogen bond between this residue. And also the second hydrogen bond comment we use to track the backbone hydrogen bond. So because the hydrogen bond could be actually created between the side chains residues, side chains of the different residues, or even backbone of the different residues. So we need to care about these two. So with the H-bond backbone, this would be a specific, guys using the same link. And also, as I mentioned, you need to, what's happened? Okay, so you need to actually use this specific comment so that you actually get the hydrogen bond for the backbone. And another things that you need to add RMSD comment to calculate backbone RMSD to the first frame as a means to track unfolding. For example, some mutation leads to some part of the protein to be unfolded. So it's not, as I write before, it's not part of the hydrogen bond analyze, but it's better to have this. So and hit run. So once you complete, you have the all complete hydrogen bonds that could get that Amber find in your system, okay? And if you interest in, for example, if you dock a ligand on a protein, you may interest in how interaction, you want to calculate the hydrogen bond between the protein and a small molecule. So in that example, suppose we have a system consists of the protein receptor with that amount, 51 amino acids and 2 zinc ion. So the ligand residues ID would be this, yes. And the trajectory that we have, it consists of this amount of the frames. So, and we pre-process, I mean to remove all the waters and remove and reorient using the auto-image comment. So we need to actually, we want to calculate the hydrogen bond in the protein and the small molecule. So first we know the trajectory and first we need to load the topology file, and you need to actually load the trajectory. And this is the hydrogen bond comment. You mean that we have this residue and we have the 2 zinc, and this is a ligand. So you need to include the residue number for the ligand so that you could calculate the hydrogen bond, analyze hydrogen bond that happened between the protein and your small molecule, and then save your actually hydrogen bond plot. Another thing that it's important to think about and do is that you have to extract a PDB file. As I mentioned, loading the trajectory file, it's a bit annoying because it's too heavy to load with the visualization. I think Amber could, not Amber, VMD software could load the trajectory file. But for example, if you want to just give a snapshot of the trajectory and see if your protein and overall system looks good and you don't see something weird happen on your system, you could actually extract a frame from your trajectory. I mean the process trajectory file. Okay, so it's so simple. You could, if you actually work with another Amber, you could first you need to actually calculate how many frames you have. You could use this comment so that this comment review and prints how many frames you are, and you could actually select uh, to tell Amber which frame you want to extract. So for example, I want to extract the final frame. I have this amount of the frame, so I went 10,000 frame. I want to extract the frame of the 10,000 of the trajectory file so that I could visualize that. So simply you use the trajectory, you use the topology file as always, and then when you want to load the trajectory file, so comment traj in and your trajectory name, and this is the name of the and the number of the frame that you want to actually interest on, and you want to extract it from the trajectory. If you want, you could actually get many frames. For example, I want to 5,000 frame. I want to extract the 5,000 and 10,000. So you could actually put the number and play with that to get the various frame from the trajectory file, and just put the auto image, and this is called the traj out. You mean the output would be name this, the final frame of, for example, KRAS PDB, and your final, your output would be in PDB format. This is the name of the format that's called Amber. You want PDB format. I'm just wrong. Okay, and if you actually in the cluster we have Amber 20 version. So if you want to use the Amber 20 version, you could simply use these comments. It gives this and it gets the last frame. The Amber 18 does not support these comments. So another important analysis that you would be interested is that how the secondary structure of the protein would be changed. As you know, that protein, that 3D protein secondary structure contain of loops, turns, helix, and sheets. Yes. So with the DSSP analyze or calculation, you could see how the secondary structure change upon a binding a specific drug or something, or upon a mutation or something. So you could use that comment to get the plot. So these plots show you how the secondary structure change. This is actually the important analyze, and also another things that I really want to mention specifically for, it's really important for some system. For example, if you want to calculate the overall surface area of the solute atoms as well as the contribution of the residue to overall surface, you could use that comment. So it just calculate the surface area. I believe that Schrodinger and Messner could actually calculate the surface area, but if you want to calculate the surface area using the Amber, you could use that comment too. This is a simple overview about analyze. So for example, the solvent accessible surface, this is the last thing that I mentioned. This is the, for example, I have a cavity or binding site, a specific binding pocket or something like that. And I want to calculate the surface area in angstrom. So I simply use that comment and give you such a plot. So you could, I use the same analyze for 3 different systems so that I could actually see how a specific mutation, for example, the green one is wild type, the red one or orangish one is the G12V mutation, I mean that I turn the glycine to the valine residue, and this is I turn the glycine to the cysteine residue. So with this analyze, you could actually see how a specific mutation could change the solvent accessible surface on the wild type mutation. Just you should compare it. It gives you the average angstrom, average surface area in angstrom, so you could calculate that. For the change in the secondary structure, I mean that, for example, this is alpha helix. You see, this is a wild type, and this is the mutation. If you see that space, I mean, this part, how to, okay, this part, if you see this part, this the red one, you see after mutation, you have another band, the band would be more stronger, you see? So these actually analyze gets you a clue to see what's happened. For example, if these create, it means okay, maybe there is a new hydrogen bond. So you could actually look for the specific hydrogen bond